In 1929, a young electrician in Barcelona, Spain, had one problem. He could not find a soldering tool good enough to do his job. His name was Jaime Benet Campabadall. He built his own tool. Nearly a century later, the company bearing his initials, JBC, operates on 5 continents, employs 148 people, and sells premium soldering equipment to aerospace, medical, and automotive manufacturers worldwide. How did one electrician's frustration build a global brand? What soldering is before? Understanding JBC, you need to understand soldering. Soldering is the process of joining 2 metal surfaces together using a filler metal called solder. The solder is heated until it melts, flows into the joint between 2 metal parts, then cools and hardens, creating a bond that is both physically strong and electrically conductive. Every circuit board inside every electronic device runs on soldered joints. Smartphones, pacemakers, fighter jet navigation systems, satellite communication equipment. Every single one of those devices exists because someone, at some point, pressed a heated metal tip against a wire and melted solder onto a board. The tool used to do that is called a soldering iron. The quality of the iron determines the quality of the joint. A bad iron means inconsistent heat, which means weak joints, damaged components, and failed boards. In industries where failure is not acceptable, aerospace, medical devices, automotive electronics, the soldering iron is not a minor tool, it is a critical one. The world in 1929. In 1929, electronics were in their earliest commercial stage. Vacuum tubes were the dominant technology. A vacuum tube is a glass bulb containing metal electrodes used to amplify and switch electrical signals. They powered radios, early telephone systems, and the first primitive computers. They were fragile, large, and required careful hand assembly. The tools available to electricians assembling these early devices were crude. A soldering iron in 1929 was essentially a copper rod attached to a handle, heated by an open flame or basic electrical resistance. There was no temperature control. There was no consistency. The operator heated the tip, guessed when it was hot enough, and hoped the joint held. That was the world Jaime Benet Campabadall worked in. The founding of JBC, Jaime Benet Campabadall was a young electrician working in Barcelona, Spain. He found the tools available to him inadequate for the precision his work demanded, and he could not find anything better on the market. In 1929, he built his own. He founded a small workshop in Barcelona, naming the company after his own initials, JBC. That company became JBC Soldering. The workshop started with one goal: build tools that professional electricians could actually rely on. By the time competitors like Weller, founded in the United States in 1945, and Hakko, founded in Japan in 1952, entered the soldering market, JBC had already been building tools for over 2 decades. JBC had a 16-year head start on Weller, a 23-year head start on Hakko. The question was whether JBC could build something those competitors could not match. The problem every soldering iron had. For decades after Jaime Benet Campabadall built his first tool in 1929, the fundamental design of the soldering iron barely changed. Every iron worked on the same principle. A heating element sits inside the handle or body of the tool. That element heats a long metal rod. The rod transfers heat down to the tip. The tip then touches the solder, melts it, and the joint is made. The problem with that design is distance. The heating element is far from the tip. Heat has to travel through multiple layers of metal before it reaches the working surface. Every layer it passes through is a barrier, a point where heat is lost before it arrives where it is needed. That distance created a specific, expensive problem called thermal drop. What thermal drop costs? Thermal drop is what happens when a hot soldering tip touches a cold circuit board joint. The moment the tip makes contact, it loses heat rapidly. The cold metal of the board and the joint absorbs the tip's temperature. On a conventional soldering iron, that drop can be as large as 70 degrees Celsius in a single contact. 70 degrees Celsius is not a minor fluctuation. It is the difference between a tip that melts solder cleanly and a tip that is too cool to do the job properly. When a tip drops 70 degrees Celsius, the operator has to wait. They lift the iron, hold it in the air, and let the heating element inside the handle work to bring the tip back up to operating temperature. That recovery can take anywhere from 10 to 90 seconds, depending on the station. In a factory where one technician solders hundreds of joints per shift, that wait time compounds. Seconds become minutes. Minutes become lost production. And because the tip spends part of every joint cycle running below its ideal temperature, the quality of every single joint becomes harder to control. In consumer electronics, an inconsistent joint is a returned product. In a medical device, it is a potential failure inside a patient's body. In an aerospace system, the consequences are worse still. The entire industry accepted this problem as the cost of hand soldering. JBC decided to eliminate it. The cartridge, putting the heat where it belongs. JBC's answer was a structural one. Instead of placing the heating element inside the handle, JBC placed the heating element inside the tip itself. In JBC's system, the tip is not a simple metal rod. It is a self-contained unit called a cartridge. Inside each cartridge, the heating element and the working surface are a single integrated piece. There is no long metal rod for heat to travel through. There is no distance between where heat is generated and where heat is applied. A fully integrated thermal sensor also sits inside each cartridge, directly alongside the heating element. That sensor reads the temperature at the exact point of contact, not somewhere back in the handle, not somewhere in the middle of the tool, but at the tip itself, where the solder meets the board. The result of that design is measurable and specific. When a JBC tip touches a cold joint, the temperature drop is 30 degrees Celsius. Competing stations drop 70 degrees Celsius on the same contact. JBC tips lose less than half the heat that conventional tips lose. What that number means in practice: that 40 degrees Celsius difference, 30 degrees Celsius versus 70 degrees Celsius, changes how the tool is used entirely. Because JBC's cartridge recovers temperature faster, operators can run their stations at lower set temperatures while maintaining the same soldering performance. Lower temperatures mean less thermal stress on the components being soldered. Less thermal stress means fewer damaged parts and fewer failed joints. The speed of recovery matters just as much as the size of the drop. JBC systems reach 350 degrees Celsius in as little as 2 seconds from the moment the operator lifts the tool from its stand. Competing stations reach that same temperature in 10 seconds at best. Many take up to 90 seconds. For a technician soldering a 200-joint circuit board, the difference between a 2-second recovery and a 90-second recovery is not a minor inconvenience. It is the entire pace of the job. The T245 handle and the cartridge range. The cartridge system required a new type of handle to go with it. JBC built the T245. The T245 is a general-purpose soldering handle designed around one principle: put the operator's hand as close to the working tip as possible. On conventional soldering irons, the grip sits far back from the tip. The operator is essentially holding a long rod and trying to place its far end onto a tiny target. On the T245, the distance between the grip point and the working tip is deliberately short. Shorter distance means more precise control. More precise control means better joints. The T245 is compatible with JBC's C245 cartridge range. The C245 range is a library of tip shapes and sizes, each designed for a specific type of soldering task. fine point cartridges for soldering tiny surface mount components, wide chisel cartridges for heavier ground plane work, bent tip cartridges for reaching joints in tight spaces. Cartridges in the C245 range can be swapped without powering down the station. A technician can change from one tip shape to another in seconds using a quick-release extractor tool. No burns, no downtime, no waiting for the station to cool. The Sleep and Hibernation system, the cartridge design, solved the problem of thermal drop. JBC's next engineering decision solved a different problem entirely: tip degradation. Soldering tips degrade through oxidation. Oxidation is a chemical process where oxygen in the air reacts with the hot metal surface of the tip, forming a layer of metal oxide. That oxide layer does not conduct heat well. As it builds up, the tip becomes less effective at transferring heat to the solder. Eventually, the tip fails completely and has to be replaced. Oxidation accelerates at high temperatures. A tip sitting at 350 degrees Celsius in a stand between uses is oxidizing rapidly. Every minute it sits hot and idle, it is wearing out. JBC built an automatic solution into every station. When the operator sets the iron down in its stand, the station detects the tool's presence and immediately drops the tip temperature to 180 degrees Celsius. This is called sleep mode. If the tool remains in the stand beyond a set period of time, the station cuts power entirely. The tip returns to room temperature. This is called hibernation. The difference those two modes make is not subtle. JBC cartridges last up to 5 times longer than tips from competing brands. That figure comes directly from the reduction in oxidation that Sleep and Hibernation produce. A tip that spends less time at high temperature while idle lasts dramatically longer than one that stays hot continuously. For a professional facility running dozens of stations across multiple shifts, tip lifespan is a direct operating cost. 5 times longer means 5 times fewer replacements and 5 times fewer interruptions to production. The result, a brand built on engineering, not marketing. By the time JBC's cartridge system, T245 handle, and Sleep and Hibernation technology were fully developed, JBC had built something that competitors could describe but not easily replicate. One professional on an electronics forum described the experience of using a JBC station for the first time as follows. The station was 5 times better than anything else on the bench, and also 5 times more expensive. That price gap was not accidental. It reflected exactly what was inside the tool. JBC dedicated approximately 25% of its entire workforce to research and development. In a company of under 200 people, 1 in every 4 employees was working on making the next version of the product better than the current one. The soldering tool market is not short of competition. Weller had been building tools since 1945. Hakko had been building tools since 1952. Both companies had global distribution, strong brand recognition, and decades of engineering experience. JBC's answer to that competition was not a lower price. It was better technology, and the cartridge system delivered it. But the cartridge system and Sleep and Hibernation only solved the problem of the individual tool. By the 2010s, the electronics manufacturing industry had developed a problem that no individual tool, however precise, could solve on its own. The problem a better iron could not solve. By the 2010s, JBC had built the most technically capable soldering tools in the professional market. The cartridge system was faster than anything Weller or Hakko produced. The Sleep and Hibernation system extended tip life to 5 times that of competing brands. The T245 handle gave operators more precision than any conventional iron allowed, and none of that was enough. The problem was not the tool anymore. The problem was the factory floor, what a modern electronics factory actually looks like. Picture a large electronics manufacturing facility, not a small workshop, a full production facility building circuit boards for medical devices, aerospace systems, or automotive electronics. That facility might have 200 technicians working simultaneously across multiple production lines. Each one is using a soldering station. Each one has their station set to a slightly different temperature. Each one applies the iron at a slightly different angle, for a slightly different length of time, with a slightly different amount of pressure. Every one of those small differences is a variable. Every variable is a potential source of inconsistency. And in a facility producing thousands of boards per day, inconsistency at scale means defects at scale. Even the best soldering iron in the world cannot fix that problem. A tool can only control what happens at the tip. It cannot control what the operator does with it. How long they dwell on each joint, what temperature they actually set the station to, or whether they are following the correct procedure for each specific product they are building. The industry had a name for the solution it needed. That name was traceability. What traceability means and why it matters. Traceability means knowing, with documented certainty, exactly what happened at every step of a manufacturing process. For hand soldering specifically, traceability means knowing which operator soldered which joint, on which board, at which station, at what temperature, for how long, using which tip, at what time of day. Every single variable recorded and retrievable. Aerospace manufacturers need traceability because a circuit board failure at altitude can bring down an aircraft. Medical device. Manufacturers need it because a failed joint inside a pacemaker can kill a patient. Automotive manufacturers need it because a defective board in a vehicle's control system can cause an accident. Without traceability, when a board fails in the field, the manufacturer cannot determine whether the failure came from the soldering process, the components, the board design, or something else entirely. They cannot identify which other boards from the same production run might have the same defect. They cannot fix the process because they do not know precisely what the process was. Before JBC Net, hand soldering had no system that could provide this. Automated soldering machines had logs and records built in. Hand soldering, the process used for the most complex, delicate, and precision-critical joints on a board, produced nothing but the joint itself. That gap was unacceptable, and it was getting worse as the electronics industry grew larger and more regulated. Industry 4.0, the framework the industry was moving toward. By the early 2010s, the broader manufacturing world was beginning to adopt what it called Industry 4.0. Industry 4.0 is the term for the fourth industrial revolution. The first industrial revolution was powered by steam. The second was powered by electricity. The third introduced computers and early automation. The fourth connects all of those systems together through digital networks, real-time data, and machine-to-machine communication. In a factory operating under Industry 4.0 principles, every machine on the floor is connected to a central system. Every machine reports what it is doing in real time to a manager who can be sitting anywhere in the world. Parameters can be adjusted remotely. Problems can be identified before they produce defects. Production data is logged automatically without a human writing anything down. By the mid-2010s, automated machines in electronics factories were already operating this way. CNC machines, reflow ovens, and wave soldering systems, all connected, all logged, all controllable remotely. Hand soldering stations were not. They were islands. Each one sat on a bench, did its job, and produced no record of anything. JBC saw that gap clearly. Carlos Sanchez, JBC's lab manager, stated the problem directly. The soldering sector was evolving by adopting Industry 4.0, and to guarantee efficient and high-quality production, manufacturers needed to decrease errors, control processes, and trace every soldering job. JBC built the answer to that problem from the ground up. What JBC Net is and how it works. JBC Net is a software system. It connects an entire production floor of JBC soldering stations to a single central management network through the internet. Here is what that means in concrete terms. A production manager can open JBC Net on a computer and see every soldering station currently running in the facility, every station's current temperature, every station's assigned operator, every station's active parameters, all of it live in one place. That same manager can configure every station simultaneously from that interface. If a new product line requires a specific temperature profile, the manager sets it once in JBC Net and it pushes to every relevant station on the floor. The operators do not need to adjust anything manually. The settings are applied automatically. JBC Net also logs every action. Every joint an operator makes is recorded. The station ID, the operator ID, the temperature, the duration, and the timestamp. When a board leaves the production line, there is a complete digital record of every soldering operation performed on it. That record can be retrieved, audited, and presented to a regulator, a customer, or a quality team at any time. For the aerospace, medical, and automotive manufacturers that JBC serves, that record is not a convenience. It is a regulatory requirement, and for the first time, a hand soldering station could produce it automatically. JBC Net also enabled something that had been practically impossible before. A factory manager in one country could monitor and adjust soldering stations in a facility in another country in real time without travelling or calling anyone. As JBC described it directly, from Shenzhen a manager could control factory lines running in Guangdong or Sichuan simultaneously. The IPC Apex EXPO Innovation Award 2018. In February 2018, JBC submitted JBC Net to the IPC Apex EXPO Innovation Award competition. IPC is the global trade association for the electronics manufacturing industry. It sets the standards that aerospace, medical, and military electronics manufacturers are required to follow worldwide. Its annual Apex Expo, held that year at the San Diego Convention Center in California, is the largest electronics manufacturing trade show in North America. JBC Net was reviewed, scored, and rated against 34 competing products and services by a panel of industry experts. The review board evaluated each submission on the uniqueness of the technology, the value it delivered to the industry, and the problem it solved. JBC Net won. The Innovation Awards Review Board described JBC Net as a pioneering software system that managed and optimized the hand soldering process, standardized parameters, and controlled operator performance. The award was presented during the keynote address by John Mitchell. John Mitchell was IPC's president and CEO. For a privately held Spanish company with fewer than 200 employees, winning the most prominent innovation award at North America's largest electronics trade show was a statement. JBC had entered a category of competition that went far beyond building a better iron. Where JBC stands today. Today, JBC operates its headquarters at Ramon y Cajal 3, Molins de Rey, in the Barcelona province of Spain, the same region where Jaime Benet Campabadall built his first tool in 1929. The company maintains branches in St. Louis in the United States, Guadalajara in Mexico, Hong Kong, Shanghai in China, and Chennai in India. Its distributor network spans all 5 continents. As of 2026, it employs approximately 148 people. Of those 148 people, roughly 25%, approximately 37 employees, work exclusively in research and development. JBC's annual revenue sits between $15 million and $27 million. Those are the figures for a company that has never chased volume, never competed on price, and never tried to be the most affordable option in the room. JBC built its business by being the most capable option and charged accordingly. The company that Jaime Benet Campabadall started because he could not find a tool good enough to do his job, now supplies those tools to the manufacturers building the most precision-critical electronics on the planet. That started with one electrician, one workshop, and one problem he refused to leave unsolved. If you found this story worth your time, a like and a subscription help more people find it, only if you genuinely enjoyed it.